Hi everyone, today my partner Yuting and I, Ganshun, are going to talk about McKean-Vlasov SDEs. This is going to be a quick introduction to MVSDEs, extending what we've covered in class so far. First, we're going to talk about the motivation behind MVSDEs and go through a toy example that will help us understand these processes. Next, we'll give the proper definition of a MVSDE and properties of its solutions. Following that, we'll look at the associated PDEs for these equations. Then we'll see how a certain Markov property no longer holds true. Lastly, we'll look at another simple example and study its invariant measure. So, the motivation. Up until now, we've looked at modeling systems with only one particle. I don't know about you, but in the world I live in has more than one particle, and sometimes those particles even interact with one another. So, what about n particles at the same time? How do we model their interactions? Let us consider n interacting particles, x sub t from 1 to n, driven by SDEs of this form. Each particle is driven by an independent Brownian motion, w sub t of I. Notice that b, the drift term, and sigma, the diffusion term, both take an additional parameter in the form of mu. This is how we encode the particle interactions on a high level by making these parameters dependent on the distribution. In this case, mu is a measure, and we define it as an average over n Dirac deltas, each placed at the position of the kth particle. Two key aspects of this system are that b and sigma functions are shared across all the particles, and that the particles have weak interactions. In essence, their contribution to the overall mu is on the order of 1 over n, which decays as n tends to infinity. To help us understand this better, let's go through a toy example. Consider this setup, where b is a function that contains an integral over mu, and sigma is just 1 for simplicity. We plug these into the equation we had earlier, which gives us an integral over deltas, and what we have is the following. For each particle, its drift term is its distance to the empirical average of all the particles in this system. Moreover, if we average the d-axis of all the particles, we get that the movement of the empirical average has no drift at all, since the drift terms will cancel out. The movement of the empirical average is simply an average of the n independent Brownian motions. Notice that as we take n to infinity, we see that the diffusion term tends to 0 due to the law of large numbers, which means that our average doesn't move. Now, let y sub t of I be the limit as n tends to infinity of x sub t of I. And let the starting initial conditions for each x be sampled IID from C of I. Substituting this in results in the following. We can then show that the expectation of y sub t of I is also constant with respect to t, and thus the expectation of y sub t of I is equal to the expectation of the initial random variable C of I. Thus, we replace C and we get this. This is our first McKean-Vlasov SDE. This equation is dependent not only on y, but also the distribution of y in time. Another point of interest is that these resulting y's are all IID in the McKean-Vlasov limit as n, not t, tends to infinity. So let's properly define these SDEs. The McKean-Vlasov SDE is defined similar to what we had before, but now with mu sub t being the distribution or law of the random variable y for all t greater than equals to 0. So what are the solutions of this system like? A strong solution to the MVSDE equation is defined as the pair of y and mu which simultaneously solves both equations above.
For any given measure mu, Unrelated to the random variable y, with Lipschitz conditions on the coefficients of the SDE, classical arguments ensures there exists a unique solution y mu. Now, define a map that takes mu to the law of y mu, another measure. Then y mu, the solution of the above SDE, is the solution of the McKean-Vlasov SDE if and only if y equals y mu and mu equals phi of mu, the law of y mu. This is very exciting. Fixed points of phi are solutions of the McKean-Vlasov SDE. The proof of existence and uniqueness is analogous to what's done in class for E2SDE. The proof of convergence for the n-particle system to the McKean-Vlasov SDE follows similar steps. In practice, the McKean-Vlasov SDE may be simulated by approximation with n particles. I was interested in the richer probability flows of interacting particles over non-interacting particles, and thus we now look at PDEs and the Fokker-Planck equation. For E2SDE, recall for any smooth test function with compact support, we can apply Ito's lemma, take expectations to get rid of the martingale term, take the partial derivative with respect to time to look at how mu changes with respect to time, rewrite the expectation as an integral against the measure mu, do integration by parts, collect all the terms to get a product of the test function and the terms of the PDE, set this to 0 for all test function to obtain the Fokker-Planck equation. I highly recommend these two YouTube videos which goes over the above derivation. Analogous to E2SDE, the measure mu in McKean-Vlasov SDE satisfy a PDE. In this case, the PDE is non-linear since mu also appears in the drift and diffusion terms. And the dependence is non-local since the drift and diffusion terms depend on mu not only at the value mu of xt, but the entire distribution mu of xt at all values of x. An example is writing the drift as an integral with respect to mu, which can be seen as an expectation of an interaction function between this particle and all other particles. A lot of work goes into deriving the above, including taking derivatives with respect to a probability measure. Please see the appendix for the Lyon's derivative of probability measures. Markov property. Recall the Markov property for E2SDE, where we can evolve the SDE from a point xs to xt. In fact, it has an even stronger Markov family property. If we solve the E2SDE for every deterministic initial point x, then average this solution according to an initial distribution m, it is the same as starting the E2SDE at a random variable with distribution m. However, this property does not hold for McKean-Vlasov SDE. Solving the McKean-Vlasov SDE with a random initial state, then conditioning on a particular initial point x, does not give the same distribution as solving the McKean-Vlasov SDE with a deterministic initial state. The law of x appears in the coefficients of the McKean-Vlasov SDE, and the law of a random variable is very different from a non-random variable. Invariant measure. Let us look at another toy example, the double well potential. Here is the E2SDE and the invariant measure. For small drifts, i.e. the low temperature regime, each particle will likely be at one of the two minimizers. For the McKean-Vlasov SDE with an added weak attraction term corresponding to mean reversion, we get a similar invariant measure. For small drifts, i.e. the low temperature regime again, the particles are likely to be in one of two wells, and transition happens when enough particles migrate over to the other well. Here we can see the particles in one of two wells. Let's kick some over to the other side and we can see that these particles pull the rest of the particles over. This video is mostly based on the crash course on making blast of SDE by Daniel Lecker, 2018. We thank Professor Mattingly for suggesting this reference. The reference we started with, the last one, is really hard to read. The second last reference is a textbook which the crash course borrows heavily from. The first reference are notes on the Lyon's derivative, and it is good to look at a topic from multiple perspectives. Any questions? Thank you! Here are some additional definitions. Bye!